Hello and welcome in this very first technical presentation of our playlist. In this video, we will hopefully cover all the building blocks of the modern fabrics that leverage VXLAN, L2VPN, EVPN. But first things first, I would like to spend some time on history and terminology. So before we go back to the slides, there are some notes and disclaimers that I do want to mention. Yeah, I do love notes and disclaimers. So this first section of the presentation about history and terminology is pretty heavy. It consists into very few slides. I think there are no more than 10, but we are going to spend quite some time in those slides, digging into them. The reason why is because this will give us the opportunity to first review all the legacy architectures, topologies, designs that we used to have back in the old times, because this will allow us to deduce all the challenges and limitations that those infrastructures used to have. And this will allow us to better understand why we needed all the enhancements that the industry introduced over time to reach the modern fabrics for data centers. And the second thing is, as we will be covering the enhancements, we will need a bunch of vocabulary terms. Those vocabulary terms will become clearer and clearer as we go further into the slides and we explore the next sections and we see the configurations and so on. But I still wanted to give global definitions so that we try to demystify the things as soon as we can. So this is why this section is a bit heavy. And the other disclaimer that I wanted to make is regarding this. So it's a pen that goes with a tablet. Actually, I had those somewhere in my home since multiple years. I never used them. And I just brought them now because I realized that if I don't draw anything, it will be more difficult to follow. So please be indulgent because it's really my very first times with this pen, and I will need to go on the other screen to do some back and forth between the pointer and the pen. So I hope it will be fluent, but sorry for the delay that I will be introduced. Well, I hope that this introduction gave you the will to continue with me. So please bear with me at least for the first section. Yeah, so what do we have on the screen? We recognize here the typical drawing that we had into all the types of networks that we were deploying back in times a few decades ago, campus, data centers, anything. We were using either a 2-tier or a 3-tier architecture where we would have, and by the way, let me take the pen, we would have one layer of access switches and then either one or two additional layers. So here we have just one additional layer of distribution/core, or we could have also on top of it another layer dedicated for the core. But now here, let's consider just this 2-tier architecture. And obviously, we use the first layer in order to connect end hosts, so the servers typically in a data center environment. Now let's remind ourselves of the responsibility of each layer. So where do we place the gateway in this kind of designs? Knowing that a gateway can be present and active at any given point in time just in one only place. So we need to carefully think about where we place it. Then we need to carefully think about how we make it redundant. Well, obviously, in this kind of topology, where we would place it would be on the distribution layer, because it is the central point of the network. So, okay, we understand that it will be carried by the switches here. But again, only one can be active at a given point in time. So how do we solve this issue? Well, we have multiple protocols to solve this, right? We would need to run a first hop redundancy protocol. And we know that there are multiple kinds of them. There is HSRP, VRRP, GLBP. They have all the same goal, that we take multiple switches, we configure on them the same SVI with the same IP address. Those switches will communicate together in order to elect one device only that will be active for the SVI at any given point in time. So this gives us this boundary for the layer 2/layer 3 separation. What does it mean for our network? It means that the first layer of switches, the layer 2 switches, access switches, sorry, they really do just this for a living, like they do layer 2 switching. So if I have this host who wants to communicate with this host, and if we assume that they are in the same VLAN, they can be switched directly locally. But if these two hosts belong to different networks, then in order to route between the two, we would still need to go to the distribution layer and go back to the access switch in order to perform the routing. Obviously, this works. It's operational. It's just that it's not efficient because we are going one hop further, one hop away in order to be able to access the layer 3 functionalities, so the layer 3 routing. It also means that if I want to connect to the outside using routing, like for example, a firewall or a router to have access to the outside environments and to the internet or whatever, then my layer 3 routing, I can connect it only to the distribution switches. I cannot connect it anywhere in my environment. So you see, we are listing multiple challenges and multiple constraints that were induced by this network. And for now, we have touched only the challenges that are brought by the placement of the SVI, right? But there are also other challenges that we will cover when it comes to the layer 1 and layer 2. So let's check this. But first, let me clear the mess on the screen and take again my pen. Okay. So what do we have from a connectivity perspective? For a moment, let's ignore that I have some lines that are in dotted lines. Let's assume that everything is in plain line. What do I have here? Well, here I just wanted actually to dual attach my layer 2 switch to the distribution switches, right? Because I want to do this to add bandwidth, to add resiliency, etc. And also, I want to do the same for my servers. Like I just want to dual attach them. It sounds a good thing, right? A good idea, again, for redundancy and for scalability. But what do I have now? Well, we are creating one of the biggest nightmares of any network engineer, which is a beautiful layer 2 switching loop. And to break the loop, not to break the loop, but to prevent the loop, we need one of the most loved and cherished protocols that ever existed in the networking field, which is spanning tree protocol, right? So what spanning tree protocol does for a living is that it will allow us to prevent switching loops, which is absolutely amazing. It's really what we want. But how does it do that? Well, it will take all the available links that we have in our topologies, all the redundancy that we built and that we would like to have. And out of all these redundant links, it will take just one active and the rest it will simply block. So it means that the additional lines that we have will remain idle. And this is why obviously they are in dotted lines into the slide. So it's not the only drawback that spanning tree has, because even for convergence, it's not very efficient. You know, it relies, if you remember, on topology change notifications when we detect the loss of one switch or the loss of one links. It will provoke the flush, of the MAC address tables. So again, same thing as for the layer 3 placement. This works, this is operational, it's just that it is very not optimal. It was good for the requirements that we had back in time. You know, it was sufficient when we didn't need that much of bandwidth, when we didn't need sub-second convergence. All this was okay. But, you know, with the evolution of the technology and as the applications started to diversify and needing more and more bandwidth, this was no longer acceptable. So we needed to come with something else, something better. And before moving to the next point in time, I just would like to add a last challenge that was brought by this kind of infrastructure. And again, let me clean the mess on the screen. Okay, and take back the pen. No, it didn't work. Okay. Erase. Pen. No. So the erase worked. The pen. Okay. So let's say now that I want, so let's say that this is my room 1 of my data center, right? And I want to add a second room that I would like to use for some disaster recovery or simply to expand my network. So what do I do usually in these use cases? Well, the first thing that comes to my mind is that I want to simply replicate my design. So I worked on it, it works. So let me replicate the design. Obviously, I will not draw everything. Otherwise, I will still be recording this first part tomorrow, which we don't want. So let me just draw one access switch and 2 distribution switches. Okay, so I have this. This is the layer 2 and this is the layer 3. So to connect the two, I would add a layer of core. Okay, this would be the core switches. And then I will connect, so I will not draw all the lines. Again, I will just connect like that. So what does it mean? It means that here I will have a kind of routing protocol, not a kind, but a routing protocol that would go between the distribution switches and the core switches. And that means that I will need to configure other SVIs there. So SVI for network 2. And here I have the SVI of network 1, for example. Okay, and then a routing protocol that allows me to route between network 1 and network 2. This could be anything in the middle. I can have OSPF, I can have BGP, I can have ISIS, I can have whatever routing protocol. And really, this for the core, it works very well. I mean, this is very good. But what if I want to take a VM that is connected there and move it seamlessly in order to connect it to the L2 switch that is present in the other room? Can I do this seamlessly? And the answer is obviously no, for 2 reasons. Because since the network 1 is only available on the first room, when I move the VM, I would need to first change its own IP address and 2, change its default gateway. So I cannot have this seamless VM mobility from room to room or data center to data center, right? So this is the latest challenge that I can think about for the legacy infrastructures. So this really comes really decades ago. So now we are going to check how we, I'm in the industry, and brilliant engineers, much more brilliant than I am, came with solutions to address all these concerns. So the first solution that came out in the industry, it is by building what we call multi-chassis, so solutions based on multi-chassis lag technology. For the data center environments, for Cisco, it was VPC, so virtual port channel. What it means here is that we now have the capability to take these 2 physical boxes, for example, that were acting like standalone and behaving like independent boxes from the perspective of the rest of the network, and instead of behaving as a standalone, now they will be showing as a single logical box from the perspective of the remaining hosts and the remaining network devices. And we can do this in any place in our topology. We can do it at the distribution layer, and obviously we can also do it at the access layer. And this is bringing huge benefits because it's allowing us to take advantage of all the available bandwidth. Because now, if I take any host, any server, or whatever it is, I can dual attach it to 2 different switches of my topology, and this will form a port channel. From the perspective of this host, again, these 2 switches, really, they are acting like just one. So the LACP PDUs that these 2 switches will send will be the same, will contain the same identifier. So this will trick the connected devices. Of course, VPC is much more complex than this, and we will have a whole section to cover VPC. For now, we are just seeing the enhancements it brings from the perspective of our previous use case. So now we are having all these links that are in non-blocking states. We are taking the advantage of all the available bandwidth thanks to this topology. This is really a great advantage, but still it has multiple limitations. So first of all, what I really would like to stress, because it's really important to have it in mind. I'm sorry, I'm not still fluent with the pen. Is that even if all these links are now plain, you know, again, that they are working, they are non-blocking, we still have STP running there. We still have STP running on the network between the the layer 2 access switches and the distribution switches. So by the way, let me call this network core. This is non-official terminology. It's just, you know, for the sake of simplicity, I will refer this to the core network. So we are still having spanning tree protocol running on our core network. It is spanning tree protocol that decided that all these links are available for forwarding. So it's still kicking in, even if at the end of the day, we are happy to have all the available bandwidth effectively usable for our traffic, but it is a decision for spanning tree protocol. What we would like ultimately as an enhancement is really get rid of spanning tree in the core. We want to have a spanning tree constrained at this boundary, you know, at this limit. So sorry, it's very messy. Let me clean it a bit. Erase everything. So what we want to be the limit for spanning tree is really there. Like spanning tree protocol, we don't want it to go further than the front ports of the layer 2 access switches. We are still not able to do it with this solution. And another limitation of VPC is that it is a solution that can take only 2 physical blocks, exactly 2 physical blocks. We cannot have a VPC of 3 or 4 switches. And the last element I would like to stress for this topology is regarding the layer 3. From a layer 3 perspective, we have almost the same limitations as we used to have in the past. Really, the only enhancements that we can introduce there is that now the 2 boxes can forward the traffic from an IP perspective. So the 2 are able to do routing. It's not thanks to HSRP, but it's a combination of HSRP and VPC that allows for the SVI to be able to route the traffic on both the boxes. And again, this we will check in more details in the sections on VPC. This is thanks to VPC peer gateway, but it's not the purpose for now. Now, just wanted to mention that here, in the opposite of the first, where we situation where we had 1 green and 1 orange from the perspective of the SVI, here the 2 boxes are green. But it is really the only enhancement that we can bring from the perspective of routing, because first, the layer 3, layer 2 boundary is still present on the distribution switches. We didn't manage to push it down to the layer 2 access switches. And second, a given network is still constrained at the distribution switch. It means that if I draw my beautiful other room and I want to, you know, allow for seamless mobility of the VMs from one room to another, well, I won't be able to do so because the network 1 is present only in the first room, and then I would need another network, so the network 2, to be present in the other room. And finally, also, if I want to attach any outside router or layer 3 firewall or something to make routing with, I would still need to attach it on the distribution layer. So long story short, it enhances a lot the situation, the VPC, but it doesn't clear all the challenges. So if we summarize, what are the challenges that we have seen into this first slide? We have seen that we had limitations when it comes to where we can, connect the outside layer 3 devices. We can do it only on the distribution layer. And we have multiple challenges that are inherent to spanning tree protocol, like the MAC flush and the blocking of redundant links. Even if the blocking of redundant links, we managed to solve and to address with VPC. We have also suboptimal forwarding, because either from layer 2 or from layer 3, by the way. We need to carefully think about the placement of the root switch for spanning tree. And when it comes to the default gateway for the SVI, we need always to go this additional hop away up to the distribution layer. We cannot do easily endpoint mobility. I mean, we can do endpoint mobility, obviously, but we need to change the IP address and we need to change the gateway, which is not very efficient. And oh yeah, there is actually a last point that I didn't mention that I'm seeing in this slide, so I remember it. It is the scalability challenge. So let's go back in the previous slide. I know that we have seen it still a lot, but there is this very last point that I wanted to address. So again, since our routing is carried by this device or even by the two, what happens if I do not have any port left on the distribution switches? Well, in that case, if I still need to connect additional layer 2 switches, I have no other choice but to remove those distribution switches and buy bigger boxes. This is what we call scale up. So we are not protecting our investment at all, because if we need to increase, if we need to go bigger, then we do not have any other choice than to replace our hardware, because we need an additional port. It's the only solution. So this is the last challenge that was worthy to mention. So I have gained the authorization to remove everything. Okay, good. Starting to be fluent, it seems. Good. So yeah, these are the main challenges that I wanted to stress. And now that we have seen the ones we have addressed, let's remind ourselves that of the ones that still need to be solved. So mainly, what we want to do now is check, I would say, two big things. How can we push spanning tree down so that it is limited at the front port of the layer 2 switches? And second, how to be able to have the default gateway available over multiple physical locations so that we have seamless mobility for our servers, for our VMs and hosts, etc. So let's head first to the first big challenge remaining. It is regarding spanning tree protocol. How can we address this challenge? And the answer, if we don't change anything in our network, meaning in the core network that we have shown previously, and let me go back to the slides. If we don't change anything here, let me take the laser or the pen. If we don't change anything there is a very simple answer to the question of how do we push down spanning tree protocol. There is no answer. It's not possible. Like if we still take the frames that are sent by an unhost and we sent it naked, meaning like as is, over the core network, then we need to have spanning tree protocol in order to allow for the proper links and to avoid switching loops. So the question is then, how do we do? What's the solution if we want to get rid of spanning tree? Is there no solution? Well, of course there are solutions, and the solutions actually lie in just one word. It is overlays. And this is the moment where I want to jump to some key terminology points, key terminology terms on which we need to be crystal clear. Because when we want to clarify what overlays are, it's important that we are clear on all the surrounding terms around these overlays. So let's go back to the slides and check. The first terminology element that I wanted to introduce is the difference between control plane and data plane. I'm sure that everyone has a good understanding and view of the difference between the two, but since it's very important, again, it doesn't cost anything apart some minutes to go over it. So the control plane roles is to act as a decision maker in data forwarding. It means that what it does for a living is building and maintaining the routing table, drawing the network topology, learning what is connected on the network, and announcing and sharing this information with the other network components, the other network devices. So just to give an idea, and just so that things get more concrete, let's consider a basic network. Oh, sorry. Let's consider a basic network with 3 routers. And every router has a loopback 0. And let's consider that we are building OSPF here, OSPF adjacencies. So OSPF obviously is the control plane protocol in our drawing. What it will do is it will, of course, we are enabling it also on the loopback. So what it will do is multiple things. First, it is responsible for building the adjacencies with the other devices. Second, it will inject the networks that are directly attached to the device. Of course, we need to do the proper configuration, like with redistribution or network or any command. It's not the purpose. What we want to say here is that we are injecting some direct information inside the process. Third, once the directly connected information is injected, it will be announced to the other devices of the network, so that every router in our topology is aware of every network that we have attached to the global infrastructure. So this is what the control plane does for a living, and here we have illustrated it with OSPF. Now we have to go to the data plane, because the OSPF, the routing protocol, builds the links and this determines what are the next hubs, but then it is the data plane's responsibility to implement the decision that was made by the control plane protocol. So it means that it acts as a decision implementer for data plane forwarding. What it means there is that, okay, let me draw again my network. So we had those 3 routers and a loopback there and there. Let's say that this is 1111 and that the loopback here is 2222. So the control plane protocol, meaning OSPF, has determined that in order to reach 2222, the next hop is this one. So it knows this. Now it's up to the data plane to take the IP packets generated by 1111 and send it over the proper interface with the proper encapsulation. And in that case, the encapsulation is simply Ethernet, and it will write in the frame, in the layer 2 frame, the source MAC address being the one of this router and the destination MAC address being the one of this router, in order to send the packet from 1111 to 2222. This is a very simple data plane, obviously, but we can have much more complex data planes. And as you can imagine, what we will see into our solutions that will be provided to the challenges of the old world is a complex data plane. It's not just as simple as IP in Ethernet and that's it. But this was for the logic of control plane versus data plane. Now we are going to move to the second terminology point, which is the difference between underlay and overlay. But first things first, I need to clean the mess. Good. And take again the pen. Okay. This is another slide where we are going to spend quite some time. So please bear with me to check first the drawing that is in the bottom. What do we have here? We have end host servers that want to communicate with each other, right? So let's call this one H1, H2, and H3. In a classic network where everything is flat, where we don't have a difference between underlay and overlay, what would happen? Well, in that kind of network, which is not the one that we are speaking about into this slide, but just to give a higher view and some perspective, if we didn't have underlay and overlay, if we had everything flat, then every device of the topology, whether it be the switches or the routers, would have the knowledge of the host, H1, H2, and H3, thanks to the routing protocol that we would make run between all these network devices. But as I was mentioning, this is not what we are speaking about here. Here we are making a difference between underlay and overlay. So the underlay would be really the real path between the network devices that makes the forwarding, meaning all the links that I am highlighting, with red. This is the underlay. And the underlay the underlay control plane purpose is to ensure that every switch on my network has the knowledge of the other ones and how to reach them. And by the way, in this context, the switch on the network, the switch on the drawing, we call them edge devices. Trying to erase. Again, apologies for that. Good. So the switches on my drawing, we call them edge devices. And the purpose, again, of the underlay control plane is to ensure that each edge device knows about the reachability to the remaining edge devices. And that's it. This is what the underlay control plane does. If you notice, I haven't mentioned anything so far regarding the reachability of the end hosts, because the information about the end hosts in this kind of designs, when we have a separation between the underlay and the overlay, it is the responsibility of the control plane of the overlay, actually, not of the underlay. So in other terms, the routers in the middle, they do not know anything about the hosts that are attached to the end devices. They do not know, and actually they do not even care about what is attached on the edge devices. It's not their job to know what is there. Their job is simply to ensure that there is proper connectivity between the edge devices and to help the control plane protocol between the edge devices and them in order to advertise, again, the edge devices reachability. That's it. It is up to the overlay control planes to learn about the end host's location, whether it is end host actually or subnets or whatever, but it is up to the overlay protocols, control plane protocol, to announce this reachability information. So far for these slides, we have talked a lot about control planes. So control plane in the underlay, control plane in the overlay. But what about the communication? I mean, obviously the data plane. How does a frame that is received on a front panel, a front port of the edge device, how is it sent through the network to reach the other edge device? So to reach the host that is connected to a remote edge device. I can rephrase the question by saying, can the edge device send the layer 3 packet as is, meaning with no additional encapsulation, no additional header, no additional treatment? And the answer is obviously no. And let me show you very quickly why it is no. Well, simply because if this router receives the naked frame, it has absolutely no idea of where to forward it, because all what it knows about is really the underlay reachability information. It doesn't know about the end devices, so it would discard it. This is why before sending any frame, the edge devices need absolutely, this is mandatory, to encapsulate the frame before sending it. And when we say encapsulating the frame, this is what we mean about, this is also what we call like tunnels, really. So there are multiple terms to designate the same thing, and let's check them into the next slide before we erase everything. So we will use the term tunnel and encapsulation to designate really the same thing. It is the virtualization network. So simply saying we are adding an extra header to the initial frame, so we are encapsulating it before sending it over the tunnel. And now what I want to mention is that the structure and the details of the encapsulation, they really vary depending on the overlay service that we are implementing, because there are multiple kinds of overlay. these on the screen are just a few of them. Some popular one that you probably heard about. I mean, probably you have worked with MPLS when it comes to L3 overlay. By the way, what I mean by L2 versus L3 overlay is simply the type of traffic that we are encapsulating. If you are encapsulating Ethernet frames, we call this an L2 overlay. If you are encapsulating IP traffic, we call this L3 overlay. And yeah, I was saying that MPLS is very popular when it comes to encapsulating L3 traffic. So usually when we are a company and we are spreading over multiple physical locations, multiple cities, usually we buy an MPLS service to an ISP, an internet service provider, that in most of the cases run MPLS. Even though now we are moving more and more to segment routing, so SR, but this is the idea. We are using an encapsulation. So we are creating a distinction and a segregation between an underlay and an overlay. And also maybe you have worked with L2 overlays like VPLS or VPWS or OTV. So these are multiple kinds of overlays. And as you might have guessed it, what we will be focusing on in our session is this one. So VXLAN BGP EVPN. And what is nice with it is that it is present into the two columns, meaning it can encapsulate whatever traffic that we want. L2, L3, it can encapsulate unicast, encapsulate multicast. It's really versatile and it's very nice because it addresses many, many needs. And also, what I wanted to mention regarding this slide and the previous slide and the previous one where we were checking, the edge devices, etc., is that so far I have tried to be as generic as possible, meaning not using any kind of terminology related to VXLAN. So for any kind of overlay, we can say that these switches on which we are connecting our end hosts are edge devices. Depending on the type of overlay that we are implementing, the edge device have specific names. For example, for MPLS, it is the PE routers. For the VXLAN EVPN, it is the VTEP, like we are going to see. But for now, we have tried to be as generic as possible. And now I would like just the last thing for our timeline before moving to VXLAN EVPN, just a quick words about another enhancement that came not long after VPC, introduced by Cisco, which is Fabric Path or Trill. So this allowed to get rid of spanning tree into our core network, since now we are no longer having spanning tree running between the edge devices and the core layer switches. Now we are encapsulating the MAC traffic, the L2 traffic, using an additional MAC header. This is why Fabric Path, we usually call it MAC in MAC. And we are replacing these spanning tree thanks to a routing protocol, control plane protocol, which is ISIS, and it is its responsibility to ensure that every edge device knows about the reachability information of the attached hosts. Just wanted to say very few words about Fabric Path. It's not at all the focus of our session. And we are moving from Fabric Path in many deployments. Well, now we reach the focus on the session. This is a very short slide to make things clear. The data plane overlay that we will be considering is VXLAN. The control plane protocol overlay that we will be considering is BGP, L2VPN, EVPN. And few benefits of VXLAN is that it allows us to have, all the enhancements that we are speaking about. We can seamlessly move one VM from one site to another, from one location to another. We can have any workload present everywhere. And also we can even add additional enhancements on top of that we didn't mention into the challenges. Like for the VLANs, we are limited to the number of bits on which we can code the VLAN. So we have a maximum of a bit more than 4K VLANs. And with VXLAN, we can go much above this limitation, since we can reach 16 million segments. And we also introduced, the industry also introduced secure multi-tenancy, meaning the capability to isolate multiple kinds of traffic, so multiple customers using the same devices. So we will dig into that as we go further. Well, now that we are crystal clear, hopefully, on the main terms, main definitions, we are able to see what does the modern fabrics look like and what is it exactly among all those possible fabrics, what kind of fabrics we will be focusing on. And you might say, okay, we have already said we are focusing on VXLAN and L2VPN, EVPN. Why? What else is it left to mention? Well, actually, Cisco has multiple implementation when it comes to VXLAN and multiple solutions for the fabrics, because we can have deployments using either ACI or NXOS standalone. So for ACI, it's a proprietary solution. It needs a controller to be able to run, which is the APIC. But it implements VXLAN. Actually, it implements a proprietary version of VXLAN. As you can see, when we compare this slide to all the other ones, we have finally made a very big improvement, is that we have moved the boundary between layer 3 and layer 2 to be present on these switches. So the way how we implement this, we need really the further sections to understand how it works. It's too early to mention it, but please keep in mind that in all the previous implementations, even with Fabric Path, we still had the layer 2, layer 3 boundary present on the above layer. Now it's the first slide where we see that the layer 2, layer 3 boundary came down. So the other two solutions, actually, it's two possibilities with NXOS VXLAN. We can either have NXOS VXLAN. Sorry, let me remove my face. We have two possible ways to leverage it. You remember in the previous slide, we said that VXLAN is the protocol in the overlay for the data plane. It's really the data plane. We can have VXLAN running without a control plane, which will be this flavor. So VXLAN float and learn. So here we have without control plane. Or we can have VXLAN running with a control plane, which obviously in this case is BGP EVPN. So please have in mind that these two implementations are possible. In our presentation, again, we will be focusing on VXLAN for the data plane, and we will have the control plane of BGP, L2VPN, EVPN. If we don't have the control plane, VXLAN can still work. We can still configure it. We can even have a look together at the CLI if it is of any interest, but we will not benefit from all the advantages that the control plane brings, meaning that if we have BGP, EVPN, when we connect the hosts or when we connect, I don't know, routers with adjacencies to the fabric, then the leaves on which we are doing the attachment will learn the information, the host information and the networks. Then through BGP EVPN, it will spread this information over the fabric. So it means that in any given point in time, the leaves already have the information of everyone. If we don't have a control plane, we rely on float and learn the same way as we rely on float and learn for a basic L2 switch. It means that a local switch, it means that if I take any switch, it will learn about its attached device when they start to communicate on the network, but it will not learn at T0 about the remote devices. For example, the switch 1 here will not have the knowledge of this host that is attached to another switch. If my first host wants to communicate to this remote host, what the VTAP will do is that it will encapsulate the frame or the IP packet and send it everywhere. Once the leaf on which the destination host is connected receives it, it will learn the source IP or MAC of the initiator and knows that it is behind the first edge. So it will update its table and forward the packet. And it's only when the return packet comes back that the first leaf will learn about where the destination was located. While in BGP, it would have learned it right from the beginning. It would not have needed to rely on float and learn to know the information. So this is just a difference. And really the last thing about this slide is that, you know, when you buy an Nexus switch, you can run it either in two ways. So either in ACI or in NXOS standalone mode. This is a choice that you make when you first bootstrap the switch. So when the switch is running in a given mode, we cannot change the mode unless we reset everything. But just to have in mind that we can switch between the two modes if we want. Like if we received a switch in ACI and we want to move it to NXOS, it's perfectly possible. It's an operation that we can do at the bootstrap of the switch. Key takeaway of this slide, we are focusing on the NXOS VXLAN fabrics using a control plane, BGP, L2VPN, EVPN. And just to put back all the pieces of the puzzle, hopefully together, if we take back, our drawing where we were showing and expliciting the difference between the underlay and the overlay, I just want to add few terms of terminology, because so far, if you remember, the devices on which we were connecting the host, we were naming them just edge device. Now I want to enter more into the details, no longer think about all the other overlay solutions, really focus on VXLAN. In the context of VXLAN, the edge device's name is VTEP, so VXLAN Tunnel Endpoint. And each VTEP has an interface that we call the NVE, Network Virtualization Edge. So interface NVE, really it will be configured like this. Each VTEP will have one interface NVE in the context of Nexus 9K switches configured for VXLAN. And then another terminology terms, when you were speaking about the tunnels that we are building between the edge devices, so between the VTEPs in our use case, those tunnels, they have a name in the world of VXLAN. It is virtual network. So the service is each service is a virtual network, and each virtual network has an identifier, and the identifier is named simply a virtual network identifier, VNI or VNID. We can find both terms into the documentations. Okay, so let me take back my pen. Then we have a very last slide coming for this generic introduction. And again, I know it is long, but I hope it was useful at least. So a very last slide where I want to explicit what kind of encapsulation VXLAN uses. Because again, we stress multiple times that each overlay solution will have its own kind of encapsulation. It will highly depend on the type of overlay solution. Well, I know I said just a second ago that I will not mention the other ones, but really just to give clarity, it's not all the overlay solutions that encapsulate in IP. For example, MPLS, they don't encapsulate in IP at all. They add on top of the naked on top of the naked packet, because it's a L3 solution for the overlays, it adds a label that requires additional protocols like LDP in order to forward the labels. VXLAN, it encapsulates the original packet or frame inside UDP and inside IP. We will see in much more details how this encapsulation works and what is the RFC behind it in the further sections. But for now, I wanted still to mention it because I want that it is crystal clear for us the role of the underlay control plane. Since we are encapsulating in IP, the underlay control plane, we understand that what it does for a living is advertising the IP addresses of the VTEPs. So we need to learn about each VTEP's IP address in order to form the tunnels. Because again, when we encapsulate inside VXLAN, the source we are encapsulating inside UDP, inside IP, and the source and destination of the IP packets are the IP addresses of the VTEPs. And just to have a clearer view of the encapsulation, let's head to the next slide, where I'm taking the original frame or IP packet, because as we have seen, VXLAN is versatile and can encapsulate anything. We add on top of it a VXLAN header. Inside the VXLAN header, we give the identifier of the virtual network segment, so the VNI. And on top of it, we are adding the UDP header quick mention about the UDP header. Again, we are going to enter into much more details in the next sections, but the destination port of the UDP header is a well-known port 4789, and the source port, it will be computed dynamically using information from the inner header. And why we do this? Simply to provide entropy and to allow for multipathing. Sorry. And then we have this outer header where we find the source IP and the destination IP of the VTEPs. So again, control plane, and the underlay control plane protocol role is to ensure that every VTEP IP address is reachable over the network, so that when we do the encapsulation, we know how to route the packet. So the network knows how to route the packet. And obviously, in the end, we have a MAC header because at the end of the day, our interfaces that connects the VTEPs to the rest of the fabric are Ethernet classic layer 3 Ethernet ports, classic layer 3 interfaces, and they rely on Ethernet for the layer 2. So we have a MAC header, which corresponds to the links MAC addresses, like we have always done in networking. So with this said, we have finally reached the end of the introduction. Thanks a lot if you have managed to wait for me till this step. So now we are going to head to really the building blocks, which is the core part of our presentation. So let's go to the building blocks.